Welcome back, my dear students. So, we will see a new session on the applications of what we have learned till now. So, I think we have in detail discussed what complex functions are, starting with complex variables, and there we have seen and mentioned some of the applications, and the major applications lie in the vector fields. So, after discussing complex functions, the analytic functions and expressing functions as mappings, we have seen what conformal mapping is, and as an example we have discussed in detail the bilinear transformation or linear fractional transformation, which you always also call as Mobius transformation. So, a vector field f of x y, if I denote it as a vector pxi into unit vector I plus qxy into unit vector j in a domain D can also be expressed in the complex form. That is, f of xy can also be written as p of xy plus I q of xy. So, here divergence of f is dou p by dou x plus dou q by dou y, and curl of f is dou q by dou x minus dou p by dou y into unit vector k. So, if we require both of them as zeros, then dou p by dou x is equal to minus dou q by dou y, and dou p by dou y is equal to dou q by dou x. So, let us see one theorem on vector fields and analyticity, so that we can understand this application better. Suppose that f of xy is equal to pxy plus qxy is a vector field in a domain D, and p of xy and q of xy are continuous and have continuous first partial derivatives in D. If divergence of f is equal to 0 and curl of f is equal to 0, then the complex function g of z is equal to pxy minus iqxy is analytic in D. Conversely, if g of z is analytic in D, then f of xy is equal to the conjugate of g of z, that is gz bar, define a vector field in D for which divergence of f is equal to 0 and curl of f is equal to 0. So, how do you understand this? So, let us quickly see the proof. If u of xy and v of xy denote the real and imaginary parts of gz, then your u is p and v is minus q. Then dou u by dou x is minus of dou of minus v by dou y, and dou u by dou y is dou of minus v by dou x, that is dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. And I know that you all remember that these are the CR equations in the Cartesian form, and this is been used to check the analyticity of a given function f of z is equal to u plus iv. The vector field f of xy is equal to minus kq by mod z minus z naught the whole square into z minus z naught may be interpreted as the electric field by a wire that is perpendicular to the z plane at z equal to z naught and carries a charge of q coulombs per unit length. The corresponding complex function is g of z is equal to minus kq by mod z minus z naught the whole square into z minus z naught conjugate, which is equal to minus kq by z minus z naught. Since gz is analytic, for z not equal to z naught, divergence of f is equal to 0 and curl of f is equal to 0. The complex function g of z is equal to az, where a is greater than 0, is analytic in the first quadrant and therefore gives rise to the vector field v of xy is equal to the conjugate of g of z, that is ax minus iay, which satisfy divergence of v is equal to 0 and curl of v is equal to 0. Coming on to potential functions, suppose that f of xy is a vector field in a simply connected domain D with divergence f is equal to 0 and curl of f is equal to 0. By the theorem which we have just discussed, the analytic function g of z is equal to p of x y minus I into q of x y has an antiderivative g of z is equal to phi x y plus I psi of x y in D, which is called as a complex potential for the vector field F. So, in the beginning of the complex variables in the introduction session, when I have discussed the applications part, we have mentioned this in that session. So, note that your g dash z is dou phi by dou x of x y plus I dou psi by dou x of x y, which is equal to dou phi by dou x of x y minus I into dou phi by dou y of x y. And so, your dou phi by dou x is your capital P and dou phi by dou y is your Q, and therefore, your f can be written as del phi, and the harmonic function phi is called a real potential function of capital F. So, let us see an example. The potential phi in the half plane x greater than or equal to 0 satisfies the boundary conditions phi of 0 y is equal to 0 and phi of x 0 is equal to 1 for x greater than or equal to 1. Determine a complex potential, the equipotential lines and the field F. See the figure and let us see the solution. We know that the analytic function z is equal to sin w maps the strip 0 less than or equal to u less than or equal to pi by 2 in the w plane to the region R given. So, therefore, f of z is equal to sin inverse of z maps R onto the strip, and the figure B shows the transferred boundary conditions. The simplified Dirichlet's problem has the solution u of uv is equal to 2 by pi into u, and so phi of x y is equal to u of sin inverse z, that is the real part of 2 by pi sin inverse z, which is the potential function on D, and g of z is equal to 2 by pi into u sin inverse z is a complex potential for capital F. Note that the equipotential lines phi is equal to C are the images of the equipotential lines capital U is equal to C in the W plane under the inverse mapping Z is equal to sin W. We found that the vertical lines U is equal to A is mapped on to the branch of the hyperbola x square by sin square A minus y square by cos square A is equal to 1. Since the equipotential lines U is equal to C, for C lying between 0 and 1 is the vertical line U is equal to pi by 2 C, it follows that the equipotential lines phi equal to C is the right branch of the hyperbola x square by sin square pi c by 2 minus y square by cos square pi c by 2 is equal to 1. Since your f is the conjugate of g dash z, and d by dz of sin inverse z is nothing but 1 by 1 minus z square the whole raised to half, we have f is equal to 2 by pi 1 by root of 1 minus z square the conjugate, which is equal to 2 by pi 1 by 1 minus z bar square the whole raised to half. The vector field Vxy is equal to Pxy plus Iqxy may also be expressed as the velocity vector of a two-dimensional steady state fluid flow at a point xy in a domain D. If divergence of V is equal to 0 and curl of V is equal to 0, then V has a complex velocity potential g of z is equal to phi of xy plus I psi of xy, that satisfies the conjugate of g dash z is equal to the vector V. So, here special importance is placed on the level curves psi of xy is equal to C. If z of t is equal to xt plus I y t, where t is a parameter, represents the path of a particle, then dx by dt is p of xy, dy by dt is q of xy. Hence, we have dy by dx as q of xy by p of xy or minus qxy dx plus pxy dy is equal to 0. Since divergence of V is 0 implies dou by dou y of minus q is equal to dou by dou x of p, and by the Cauchy-Riemann equations we have dou psi by dou x is equal to minus dou phi by dou y, which is equal to minus q, and dou psi by dou y is equal to dou phi by dou x, which is equal to p, and all the solutions of the equation satisfies psi of xy is equal to c. The function psi of xy is called a stream function, and the level curves psi of xy is equal to c are the streamlines for the flow. So, you have seen how the function, the analytic function is now related to the vector fields and the steady state fluid flow. The uniform flow in the upper half plane is defined by V of xy is equal to a 1 0, where a is a fixed positive constant. Note that mode V is nothing but a, and so a particle in the fluid moves at a constant speed. A complex potential for the vector field is Gz is equal to Az, which is equal to Ax plus Iay, and so the streamlines are the horizontal lines, Ay is equal to C. So, in the figure you can see this, and note that the boundary y equal to 0 of the region is itself the streamline in this case. So, another example, the analytic function Gz is equal to z square gives rise to the vector field V of xy is equal to the conjugate of g dash z, which is 2x comma minus 2y in the first quadrant. Since z square is equal to x square minus y square plus I times 2xy, the stream function is psi of xy, that is equal to 2xy, and the streamlines are the hyperbolas 2xy is equal to c. See the figure. So, let us see the theorem statement which is on the streamlines. Suppose that g of xy is equal to phi xy plus I psi xy is analytic in a region capital R, and psi of xy is continuous on the boundary of R. Then V of xy is the conjugate of g dash z defined and irrotational and incompressible fluid flow in R. Moreover, if a particle is placed inside R, its path z equal to z of t remains in R. So, this is a theorem which helps you to connect the streamlines. So, as an example, the analytic function Gz is equal to z plus 1 by z maps the region R in the upper half plane and outside the circle mod z equal to 1 onto the upper half plane V greater than or equal to 0. The boundary of R is mapped onto the u axis, and so V is equal to psi xy, that is y minus y upon x square plus y square is 0 on the boundary of R. The next figure shows the streamlines. The velocity field is given by the conjugate of g dash z is equal to 1 minus 1 by z bar square, and so g dash of r e raised to I theta, the conjugate of this is equal to 1 minus 1 by r square e raised to 2 I theta. It follows that V is congruent to or equivalent to 1 0 for large values of r, and so the flow is approximately uniform at large distance from the circle mod z equal to 1. The resulting flow in R is called the flow around a cylinder. So, see the graph or see the figure which will help you to understand it better. So, as an example, let us see an analytic function f of w is equal to w plus log w plus 1, which maps the upper half plane v greater than or equal to 0 to the upper half plane y greater than or equal to 0, with the horizontal line y is equal to pi and x less than or equal to 0 deleted. If g of z is equal to f inverse z, that is equal to phi of xy plus I psi of xy, then gz maps R onto the upper half plane and maps the boundary of R onto the u axis. Therefore, psi xy is equal to 0 on the boundary of R. It is not so easy to find an explicit formula for psi of xy. The streamlines are the images of the horizontal lines v equal to c under z equal to f of w. If we write w is equal to t plus ic, c greater than 0, then the streamlines can be z equal to f of t plus ic, that is equal to t plus ic plus log of t plus ic plus 1, that is x is equal to t plus 1 plus half of log t square plus c square, and y is c plus argument of t plus ic. See the figure. Next example is an analytic function f of w is equal to w plus e raised to w plus 1, which maps the strip 0 less than or equal to v less than or equal to pi onto the region R shown in the next figure. Therefore, gz is equal to f inverse of z, which is equal to phi xy plus I psi xy, maps R back to the strip and maps the boundary line y equal to 0 onto the u axis and maps the boundary line y equal to pi onto the horizontal line v equal to pi. Therefore, psi of xy is constant on the boundary of R. The streamlines are the images of the horizontal line v equal to c, where c lies between 0 and pi, under z is equal to f of w. If we write w is equal to t plus ic, then the streamlines can be z equal to f of t plus ic, that is nothing but t plus ic plus e raised to t plus ic plus 1. So, you get your x as t plus 1 plus e raised to t cos c and y as c plus e raised to t sin c. So, you can see it in the next figure. So, what have we seen in this session? We have seen some applications mainly in the vector fields, how analyticity and vector fields are related. We have seen some theorems which helps you understand better the relation between the vector fields and also the streamlines. We have done some examples where you have actually calculated the streamlines for the given function, for the given analytic function, and the corresponding graphs were also seen. I hope you all have enjoyed this session, and with this we conclude the sessions on complex variables and conformal mapping. So, we have started with defining complex variables, then we moved on to analytic function, defining it, checking the conditions for analyticity both in Cartesian system and also in the polar coordinate system. Then we have seen what harmonic functions are, what are the conditions that are satisfied by harmonic functions, the Laplace equation that is required to check the harmonic functions both in the Cartesian form and in the polar form. Then we have moved on to how to find the harmonic conjugate if a given harmonic function is in variable x and y or else in the variable r and theta. So, apart from using the analytic property and finding the conjugates, we have also learned an alternate method, that is Milne-Thomson's method, to find the analytic function f of z if either u is given or v is given, or else u plus v or u minus v is given, not necessarily any linear combination of u and v are given. Still you can find the analytic function f of z u plus iv. So, Milne-Thomson method helps you to find the analytic function, and from there you can find the conjugates, harmonic conjugates. If u is given, you can get the corresponding v and vice versa. Also, we have seen that the analytic functions, whenever fz is analytic, u equal to a constant and v equal to a constant with the normal notation, represents orthogonal trajectories. Then we have seen how to express a given analytic function or else given complex function as mappings. We have seen so many examples. We have seen what the basic transformations are and what conformal mapping is, and as an example we have discussed the bilinear transformation, seen the properties of bilinear transformation, what are its fixed points, how to find them, and also now in this session we have learned what are the applications, main applications of analytic functions and the mappings clubbing together. I hope this was a fruitful session for you, and I wish you all success. Thank you.